Hi, I'm Andy Campbell. Welcome to Standard Deviant School Nutrition. Our program today is macronutrients, protein. Here's what we'll cover.
We'll start off with a simple question. What is protein? Then we'll see how protein is digested, and we'll find out some cool things it does. After that is protein deficiency, and we'll wrap up with vegetarianism. Good jerky.
Protein, along with fat and carbohydrates, make up the 3 macronutrients your body needs for energy. Protein supports a lot of vital functions, but it's no more important than fat or carbohydrates. Proteins are made of chains of molecules called amino acids.
Amino acids are the building blocks of protein. Chemically speaking, they have a central carbon atom, C, with a hydrogen, H, an amino group, NH2, an acid group, COOH, and a side group. This side group or side chain is the only thing that changes in the chemical structure to make up one of the 20 common amino acids. That makes proteins more complex than either carbohydrates or lipids.
This is only a rough analogy, but if you think of an amino acid as a pipe cleaner, then a protein is like a chain of pipe cleaners connected with each other. See? Here's the amino acid. Here's the protein. Depending on which amino acids are connected, the protein can take a shape, like a ball, a stick, or one of many intricate structures. In contrast, say we wish to see what a carbohydrate looks like. Well, if this pipe cleaner represents a glucose molecule, a carbohydrate would look just like this. Just one long chain of glucose molecules. Clearly, you can see how much more complex proteins are than carbohydrates.
Like we said, there are 20 common amino acids, so the variety of possible sequences is enormous. Most proteins contain at least 30 amino acids, and some may have more than 300. Amino acids are connected to each other with peptide bonds. These amino acid bonds have names depending on the number of amino acids.
Peptide bonds. Peptide bonds have nothing to do with the pep rally or the tides of a sea. A peptide bond is merely a link between 2 amino acids.
A dipeptide is 2 amino acids bonded together, while a tripeptide is 3. A string of 4 to 9 amino acids bonded is called an oligopeptide, the prefix oligo meaning few. A group of 10 or more is called a polypeptide, the prefix poly meaning many. Polypeptide chains twist into various intricately coiled shapes.
When you eat proteins in food, you may think that the proteins go straight to the places they're needed in the body. That's not what happens, though. When you eat food protein, your body breaks down the food proteins to amino acids and uses those amino acids as raw materials for its own proteins. We'll explain protein digestion in the section coming up.
Now that we know the structure of protein, let's see what happens to it once it gets into that remarkable body of ours.
Mechanical digestion of protein begins in the mouth where it is crushed and moistened, and chemical digestion begins in the stomach. Hydrochloric acid in the stomach changes protein strands in such a manner that digestive enzymes can break the peptide bonds that hold the amino acids together.
When polypeptides, which are 10 or more amino acids bonded together, enter the small intestine, enzymes hydrolyze them into shorter peptide chains. Enzymes that hydrolyze protein are called proteases. Ase means enzyme. So just take the beginning of protein, prot, and add ase to get protease. A good example of a protease is pepsin, which is released by the stomach and begins to break down the protein into smaller units and amino acids. These cells absorb single amino acids and split groups of amino acids into single amino acids. Then those amino acids are released into the bloodstream to help make protein in the body in order to build tissue.
Now that we know how protein is incorporated in the body, let's look at some of the roles it plays in bodily functions.
Proteins are intimately involved in the growth, repair, and replacement of tissues. Proteins are the building blocks of the human body from the time of conception to death. Proteins are important in most body structures, such as skin, tendons, membranes, muscles, organs, and bones.
Enzymes are proteins too. So without proteins, we wouldn't have enzymes in all the useful things they do, like digesting food and fusing together substances.
Proteins are critical in the immune system. Antibodies are large protein molecules that inactivate foreign substances, protecting the body against disease.
Proteins are buffers that help to maintain the acid-base balance of body fluids. They also function as carriers to transport substances such as oxygen throughout the body. And finally, protein, as one of the energy-yielding nutrients, provides some fuel to the body, up to 4 kilocalories per gram.
And when carbs and fats are not good enough to get the job done, in emergency situations that is, you need a tissue-building nutrient like protein to step in and provide energy. Although, I must admit, it may not be the most efficient way to go. Protein provides a modest 4 kilocalories of energy. It works similarly to carbohydrates, but energy is not its main purpose. Building tissue is. 15 to 20% of the kcalories in a healthy diet should come from protein.
About 9 of the 20 amino acids are what we call essential. In other words, the body cannot make them, so they're essential to the diet. A complete protein contains the 9 essential amino acids in the same proportion that they're found in the human body. Most animal proteins are complete. Most plant proteins are incomplete.
Overall, plant proteins are of lower quality than animal proteins. This forces vegetarians to combine plant protein foods that are complementary so that the combination supplies the full range of essential amino acids. This is called mutual supplementation or protein combination. It used to be thought that this was critical for vegetarians at every meal. Now it is believed that eating a variety of proteins throughout the day is sufficient.
Proteins that are easily digested are referred to as high-quality proteins. Eggs are one of the most complete and digestible proteins. Therefore, they're an extremely high-quality protein.
We all need protein in the right amounts. Let's see what happens if you have too much or too little protein in your body.
The most widespread form of malnutrition is protein energy malnutrition, PEM. This is commonly known as protein deficiency. PEM is common among children in developing nations. In the United States, PEM occurs often among the homeless, the poor, the elderly, and those with addictions to drugs and/or alcohol. PEM leaves individuals particularly vulnerable to infections. These infections and other problems associated with PEM, such as fever, electrolyte imbalances, and anemia, often lead to heart failure even among children.
On the other hand, excess protein consumption offers no known health benefits and may pose health risks. The research is not definitive here. It's difficult for researchers to separate the effects of excess protein from the effects of the excess saturated fat that comes with it. The recommended amount of protein is 0.8 grams of protein per kilogram of body weight. For athletes and people who exercise, however, the recommendation goes up to 1.5 to 2 grams per kilogram of body weight.
Any energy-yielding nutrient in excess, even protein, can contribute to obesity. High-protein diets are rarely successful in sustained weight loss.
Now it's time for the Broccoli and Chicken Show.
Hey, Broccoli. What? Knock, knock. Who's there? Vegetarian. Vegetarian who? Vegetarian who's going to eat you.
A person who does not eat meat is called a vegetarian. Vegetarians, especially vegans, need to plan their diets more carefully than non-vegetarians do. We all need the same type of nutrients, but vegetarians have fewer foods to choose from.
There are different types of vegetarians. Vegans, or pure, strict, or total vegetarians, exclude all animal-derived products from their diets. They consume no meat, fish, poultry, eggs, or dairy products. They only eat fruits, vegetables, and grains. Those vegetarians who consume dairy products but no other animal-derived products are called lacto-vegetarians. Lacto means milk. Remember, milk sugar is lactose. Vegetarians who consume dairy products and eggs, but exclude all other animal-derived products, are lacto-ovo-vegetarians. See the ovo there in between the lacto and the vegetarian? Ovo means egg. Sometimes people are referred to as semi-vegetarians or partial vegetarians if they exclude animal-derived foods such as red meat.
The health benefits of vegetarian diets are many and varied. Although vegetarians are in general healthier, no one can be sure if that's attributed to diet or lifestyle. That is, vegetarians tend to exercise more, use less tobacco, and moderate their use of alcohol. Although it is possible to have a high-fat vegetarian diet and gain weight. So, it's not clear to what degree vegetarianism contributes to their commonly healthier body weight, lower blood pressure, and reduced rates of heart disease and cancer.
Vegetarians need to plan properly in order to obtain adequate nutrients. Lacto-ovo-vegetarians, those that consume some dairy products and eggs, do not need to be as concerned about these deficiencies. This diet is safe even for children. Strict vegetarian diets provide the most difficulty for children and pregnant or lactating women. They also risk deficiencies of calcium. Vegetarians need to ensure they obtain adequate vitamin D and vitamin B12 from soy milk and adequate iron and zinc from fortified sources such as breakfast cereal.
Let's go over proteins one more time to make sure we've got it. Protein is an energy-yielding macronutrient. Proteins are made up of chains of amino acids, the building blocks of proteins. There are 20 amino acids in nature. They all have a central carbon atom, C, a hydrogen, H, an amino group, NH2, and an acid group, COOH. But their side groups are all different. Proteins help form most of the parts of the body, like skin, muscle, and bones. They also help digest food, protect you from disease, and a whole lot of other things too. Protein energy malnutrition, PEM, is a problem in many developing countries and for the malnourished here in the United States. Vegetarians don't eat meat. Vegans exclude all animal-derived products from their diets.
Well, that's all the time we have for today on Standard Deviant School Nutrition. We hope you learned a few things about protein along the way. I'm Andy Campbell. Thanks for watching. And happy eating.
If you've already learned about carbohydrates, fats, and proteins, check out this bonus review of the digestion process. It covers the digestion of the 3 macronutrients from start to finish.
Okay, so we've looked at how carbohydrates, fats, and proteins work in our bodies. But let's see how they work together in the digestion process. After all, how often are you going to eat a bowl of butter or a loaf of bread by itself? So, let's follow some food through the digestive tract and see how all of the digestive organs work together to get the job done.
Suppose you've taken a bite of a ham sandwich. This tasty bite of food contains fat, protein, and carbohydrate. Once in your mouth, you begin chewing the food. Enzymes in the saliva begin to break down the carbohydrate into smaller sugar units, while a pancreatic lipase enzyme for breaking down the fat is released from the tongue. The food bolus travels down the esophagus to the stomach. In the stomach, another lipase is released to work on the fat. So the 2 lipases now begin to break down the fat into smaller units. At the same time, pepsin, an enzyme which breaks down protein, is released and begins to break down the protein into smaller units and amino acids.
The food next passes into the small intestine where the major digestion and absorption of nutrients occurs. The pancreas releases pancreatic amylase into the small intestine, which breaks down carbohydrates into simple monosaccharides or disaccharides. Special enzymes released from the intestine walls break down the disaccharides into monosaccharides, and these simple sugars are absorbed.
The pancreas also releases lipase into the intestine, which breaks down the triglycerides, molecules of glycerol with 3 fatty acids attached, into separate fatty acids and glycerols. Bile is made in the liver and stored in the gallbladder. When it enters the small intestine, the bile helps the fat become more soluble so the lipase enzyme can do its job of breaking down fats into fatty acids and glycerols. The fatty acids and monoglycerides are now absorbed into the intestinal walls. The pancreas also releases protein-breaking enzymes into the small intestine. These enzymes break down the protein fragments into short peptides and amino acids, which can be absorbed by the intestinal cells.
The absorbed sugars from the carbohydrate enter the bloodstream. The amino acids from the protein travel to the liver through the portal vein, which is the vein that carries blood from the GI tract to the liver, where the amino acids are converted to glucose, fat, or put back into protein structures. In the small intestine, the fatty acids from the fat are packaged into chylomicrons, which take lipids from the intestinal cells into the body. The chylomicrons enter the blood through the lymphatic system.